All right, in continuing with our introduction to linear programming, we're going to learn how to solve very simple two-variable linear programs using graphical techniques. The end goal is that by doing this, we're going to learn a little bit about the structure of the solutions as they relate to the formulations, and it will be helpful once we get to the simplex method. So to begin, we'll start with our toy factory problem. So this is the setup that we have, and in fact, I think there's a mistake here. And this is the setup for the problem. And what we're going to do is we're going to represent this feasible area by drawing out all the lines and finding the set of points that satisfy all these equations concurrently at the same time. So the process for doing this is pretty straightforward. Basically, we want to draw the lines and then figure out which half or which side of the line satisfies the constraint or does not satisfy the constraint. So to start, we'll start with this first constraint here. All right, so if 2x1 plus x2 is less than or equal to 100. Now, usually the easiest way to calculate or draw these lines is to calculate the X-intercept and the Y-intercepts. And we can do this pretty easily just by setting x2 equal to 0, and then we solve for x1. And we sort of pretend like it's an equality constraint. So here in this case, if we solve for x1, then we'd get 50. If we repeat the same process again, but this time we set x1 to be 0, then that means x2 is equal to 100. So when we do that, that allows us to sort of mark off the intercepts. So that's the first intercept, and then the next one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, is right here. And we're just going to draw a line connecting them. All right. Oh, that's actually pretty good. All right. So now the only question is which way or which side of the constraint is the feasible set. So is it all the points on this side that are feasible, or is it all the points on this side? Okay. So the quick test that I like to do is just to plug in 0, 0 and to see if the constraint is satisfied. So we have 2 times 0 plus 0 is less than or equal to 100. That just gives us 0 is less than or equal to 100, which is certainly correct. So the point 0, 0 right here certainly satisfies the first constraint. With that knowledge, then, we know all the points sort of below the line satisfy the constraint. Okay. So everything in this direction. All right, so that's our current feasible space, just defined by that first constraint. All right. So with the next constraint, we have x1 plus x2 is less than or equal to 80. And again, we can sort of repeat the same process. So we find the intercepts, and in this case, it's a little bit easier because we know if we set x2 equal to 0, then x1 is 80. Similarly, if we set x1 to 0, then x2 is equal to 80. So let's go ahead and we can draw the line going through 80, 80. All right, and we can do the same thing. We want to figure out which side of this red line is feasible or infeasible. And again, if we stick in 0, 0 for x1 and x2, 0 plus 0 is less than 80, and that absolutely satisfies the constraint. And so we know that anything below the line satisfies the constraint. Okay. And again, this is constraint 1, this is constraint 2. All right, so we got the two constraints drawn out. The only one that really, there may be more complicated one that remains is this x1 is less than 40. And so we can go ahead and draw that in. That's pretty easy. 10, 20, 30, 40. And we got our line. And all the feasible points are to the left. Okay. The last constraints that we have are non-negativity constraints. And so they're going to, let's say, support or sort of cut off the space from the bottom. All right, so that's the first one. And we'll have another one that ensures x1 is greater than 0. And so these are the two lines that we end up with. Okay, and again, in this case, they need to be, x2 needs to be greater than 0, and x1 needs to be greater than 0. And so the intersection of all these half spaces, right, gives us the feasible set corresponding to these constraint equations. And so we can draw them in, sort of figure out what that feasible space is by drawing it in. And again, it's everything that is between the lines according to the constraint inequalities. All right, so this yellow area is our feasible space. Okay. All right, so the next question is, if we know our feasible space, where in this yellow area is the optimal solution? So the easy way to sort of understand how to do this is to think about isolines. All right, so I'm going to draw some isolines. And the isolines are going to represent solutions that all have the same z value, or value for the objective function. Okay. So one way we can think about this is, well, if x1 is 10 and x2 is 0, so we have a line right here, a line that goes through 10, 0. What is the corresponding value for x2, right, when x1 is 0? So actually, maybe we can even pick a better one. So usually the best ones that you pick are a common multiplier. So here we have 3 and 2. So sort of the easy number to pick might be like, let's start with 60. Okay. So when z equals 60, one solution is x1 is equal to 20 with x2 equal to 0, right? Or x1 equals 0 and x2 is equal to 30, right? So this right here defines an isoline for the value of z equals 60, which corresponds to the objective function. So I'm going to go ahead and draw that isoline here. So we're going to start at 20, and we're going to go up to 30. Okay. So here goes one isoline, right, that corresponds to z equals 60. That means any x1, x2 solution that lies on this line has the same value for the objective function. Okay. You know, now as we move the objective function over, right, so here we're at 50 for x1. So I'm going to sort of draw this point. Oh. So right here we're at x1 equals 50 and x2 equals 0. All these points on this line segment have the same value, right? And so we can figure it out by just plugging that line in. Right? So 3x1 plus 2x2. So that's going to have a value of z equals 150. If we look at the corresponding x2 value, so we have 1, 2, 3, 4, 6. The other solution that we have is x1 equals 0 and x2 equals 60. So if I did this right, oh no, 120. How did that happen? Oh, that's because that's 40. Sorry, that should be 40. So that should be 120. Right. So if we plug this in, we get z equals 120 again. So anything on that line has the same objective value. So effectively what we're doing when we optimize graphically, we want to take this isoline and see how far we can start moving it up and still have a solution in the feasible space. So let's try to do that. So I'm going to take this isoline. I'm going to put it right here. So at this point, our solution is 0. If we move it, let's say right here, it looks like we're crossing the boundary at 20, right? So our solution is 60. All right. If we're right there, we're crossing it at 30. x1 equals 30. So if you see my mouse cursor, and we're just going to keep shifting over, right? So when we get to this point, our solution can still be any point along the line, right? But we don't really have such a great way of telling what the value is. Here we can maybe use the x2. So 10, 20, 30, 40, 50, 60, 70. So here the solution is about z is equal to 140. But we see we can still keep moving this isoline further and further up. And in fact, we can move it to about here. And this at this point, oops, right here is the last time that the isoline is still in the feasible space. Okay? And this is actually what's going to define our optimal solution. So if we look at the coordinate system or the coordinate frame, we can sort of figure out what that point corresponds to. So here it's x1 equals 20 and x2 is equal to 60. All right? And we can just plug these values back in to our cost equation. And I should put a star here because this is going to be the optimal solution. So that's 60 plus 120 equals 180. All right, so this is our optimal solution. All righty. Now, after we found our solution, it's useful to determine which of the constraints, of these constraints right here, which of them are active, which of them are holding back our maximization problem from being even bigger. Right? So those constraints that are holding back our solution we call active or binding constraints. Okay? And so from the graphic, or from the graph, we can kind of see that the lines 1 and 2 are what's holding back our isoline from moving up further. So here we would say constraints 1 and 2 are active, while constraints 3, 4, and 5 are inactive. Okay. And again, sometimes this is called binding. Oops. Or non-binding. Now, the neat thing about this is, let's say we were to solve this problem again, but we got rid of these 3 constraints down here. Let's just say I wanted to solve that problem. I'd actually get the exact same solution, because what happens is these 3 constraints, they actually don't constrain the optimization. They're inactive. They don't really matter. So that's sort of a neat little property that we have. Okay, so I'll give a little bit more of a formal definition. All right. So we say a constraint is binding. Actually, maybe I'll type this in because I have terrible handwriting. A constraint is binding if the left-hand side and the right-hand side of an inequality constraint are equal when the optimal solution or optimal value, we can say optimal solution or optimal values of the decision variables are substituted back into the constraints. Okay, so this is perhaps a little bit more formal definition, or some sort of definition or rule that tells us if a constraint is binding or active. Right? And again, if this is not the case, then we call the constraint inactive. Okay, so let's sort of check that out. So we're going to sort of verify that. Let's just do it for constraint 1, that is in fact active. Right? So we have 2x1 plus x2 is less than or equal to 100. Right? So if we start plugging things in, we can phrase it as a question. Right? We get 40 plus 60. And sure enough, we end up with 100 equals 100. So this tells us that constraint 1 is in fact active. Similarly, we could go through the same process and you would see that constraint 2 is active. And if you tried that with constraints 3, 4, and 5, you would see that they're inactive, right? So we can just take this first case here. x1 is less than or equal to 40. If we plug in our optimal solution, we get 20 is less than or equal to 40. They're not equal, the left-hand side of the constraint with the right-hand side of the constraint. Okay, so we know, again, these guys are inactive, while the top 2 constraints are active or binding constraints. Now, before we move forward, we're going to introduce a couple useful definitions that are going to come up over and over again. The first one is the idea of a convex set. Right? So the definition here, it's pretty understandable, but when I draw out what a convex set is, I think it'll click for mostly everybody. So we say a set of points is convex if we can draw a line between any 2 points in that set, and that line is still in the set. Now, mathematically, that's just represented by the equation here. So let's sort of give an example of that. So I'll draw a circle, and the idea is I can pick any 2 points, all right? And if I draw a line connecting them, then any point on that line is still within the set, still within the circle, right? So all sorts of shapes, right, have this property. Polygons do, or a lot of them do, right? You can pick any 2 points, and no matter what 2 we pick, if we draw a line connecting them, they'll still be in the set. So these are all, these are examples of convex sets. Now, certainly the last problem that we worked with, in the toy factory problem, if we look at this area right here, right? So this yellow area, this is certainly a convex set, right? I can take any 2 points in the set and draw a line connecting them, right? And that line is still fully contained within that yellow region. I can't get outside of the yellow region. So what would be an example of a non-convex set? Well, usually they tend to be a little bit funny shaped. So let's say something like that. That would certainly be non-convex, right? I could pick a point here and a point here, and yeah, sure, part of it would be inside of the set, but if I connect the line, we see that line connection is outside of the set. And so here this would be an example of a non-convex set. Okay. There's lots of non-convex sets, of course. So another example would be, let's say, a donut, right? Let's say we wanted to find everything inside of the yellow region here, right? So there's our feasible set somehow, okay? You know, you could pick 2 points, draw a line connecting them, right? But for part of it, it would be outside of the set, and for that reason, it would be non-convex. You do need to be careful, because even though a circle is convex, right? So this might be something like, if I wanted to represent this as an equation, I might say something like x1 squared plus x2 squared is less than or equal to 25. And so that would be the set of all points centered at 0, 0, with a radius, with a circular radius of 5. So any point that's within 5 of the origin, right? Okay. So that would certainly be a convex set. Now, what wouldn't be a convex set is if I said x1 squared plus x2 squared is greater than or equal to 25. So in this case, you know, we draw our axes and then we draw our circle. What we'd be talking about is anything outside of the circle. That would be the corresponding feasible space. And of course, I could select 2 points, right? That point is inside of the feasible space. It satisfies the constraint x1 squared plus x2 squared is greater than 25. And certainly this point would satisfy that constraint. But if I draw a line connecting them, there's a part right here where that line is not inside the feasible space. And for that reason, this set is also non-convex. Okay. Now we're going to learn a very interesting property, which is that all linear programs, whether they're one-dimensional or 100-dimensional or infinitely dimensional problems, well, maybe not infinitely, I don't know what that would look like, but you know, very large dimensional problems, the feasible sets are always convex. So this is great news, or it will be great news, especially when we learn the next point, or the, oh, you can kind of see the giveaway, but the next thing, the next idea related to convex sets has to do with this idea of extreme points. Okay, so an extreme point is basically any point where if you draw a line through it, then that point has to be an endpoint. Okay, so what do I mean by that? Okay, so let's take our little triangle again. So we know there's a convex set, and I'm going to pick a point P right here, and I'm going to draw a bunch of lines that go through that point P, right? They don't even need to go to the boundary. They just have to end at P. And you'll notice for this point P, right, any point that passes through it, all right, is and fully contained within the red set, right, the set S, right, has P as an endpoint, right? There's no way to draw a line that's fully contained in S where P isn't an endpoint, right? So these points we call extreme points. Right? So in this case, this triangle would have 3 extreme points. If we want to, we can pull back. Let's see if we can. In the toy factory problem, we have 1, 2, 3, 4, 5 extreme points. Okay. And the big hint here is if you look at it, you see that the extreme point happens to lie where one of the solutions is. Okay? Or the solution, the optimal solution is. And in fact, this is the great thing about convex sets when we have a linear program, is that for these linear programs, the optimal solution, if one exists, is always located at an extreme point. Okay, and we're going to use this as part of the simplex method, because effectively what the simplex method is going to do is it's going to hop around all these extreme points to try to find the optimal solution. So first it'll go here and say, hey, is this an optimal solution? No? Well, I'm going to jump to the next extreme point. So maybe I'll go down here. Is this an optimal solution? No, I'm going to go to the next extreme point. So then it's going to go right here. And it will cycle through all the extreme points until it finds the best one. Now, the simplex method does this in a very smart way, so it can actually do it pretty quickly, right? So it's not just guessing randomly in which direction to go. All right, so that's the main takeaway of why we want to learn about convex sets, extreme points, is because ultimately all linear programs, the feasible set is a convex set, right? That convex set has a bunch of extreme points, hopefully. And if we do have an optimal solution, then the optimal solution is going to be at one of those extreme points. Now, we can apply this graphical method to minimization problems as well. Pretty much the same idea. So we're going to start by going ahead and drawing our feasible set. So I'll just go ahead and mark through some of these lines. Seven divided by 4. Right. And then, this is at 14, so it's going to be way up here. So that might be a little bit off, but I think we get the idea. Yeah, something like that. Okay, so that will be our first line. So that's for the first constraint. Moving on to the second constraint, we have 2x1, 12. Oh, wait, but we have to figure out the directionality, right? So again, we can plug in 0, 0 here. So 0 plus 0 is greater than 28. That's not true. So we know 0 is not part of the feasible set. Instead, the feasible set points upwards. So everything here is feasible. Okay, moving on to the next equation, we'll go ahead and draw our feasible set. Again, it's somewhere a little bit further out, and it should look something like that. At this point, we can do the same test where we plug in 0 and 0, and we see 0 plus 0 is not greater than 24. So in fact, our feasible set lies above the line. Now, our non-negativity constraints are pretty straightforward. So again, we have them. x2 has to be greater than 0, and so that's everything above the line. And likewise, x1 has to be greater than 0. And so that's everything to the right. So when we put this all together, our feasible space more or less takes up everything here. Now we do have to be a little bit careful because it's always going to remain on the positive side, both in the x1 and x2 dimension. So let me draw that a little bit better. So again, our feasible space looks something like this. And of course it goes up to the line. And it always stays above 0 in the x1 and x2. Now, unlike the maximization problem and the minimization problem, our goal is to lower the isoline as much as possible. So let's go ahead and draw in our isoline. So one neat little trick is you can see there's a 2-to-1 ratio here. So the isoline's going to more or less follow the same property. And so I'm just going to start drawing this in. So our isoline looks something like this guy. All right. Where it takes 2x1 to equal 1 of the x2. Oh man, keep having to move this around. All right, so here goes our isoline. Let's make it nice and dark. So the problem is we have a minimization problem. So instead of moving the isoline upwards, we're going to be moving our isoline downwards. And the question is, how far can we move this until we're just at the edge of the feasible set? And you can see it sort of happens right about here. So this is where our feasible set is. So using this graphical method, we can identify where our solution is. Now, the neat thing to notice about this is that you'll see in the minimization problem, when we're trying to sort of push our isoline down, we have these constraints, again, the red lines, that are holding it up. In the maximization problem, it's sort of the opposite, right? So you can see here, our isoline, we want to move it up, okay? But we have the constraints that are holding it back, holding it down. And so this is something to keep in mind whenever you formulate a problem. All right. Okay, so we know how to solve minimization problems. Another sort of common sort of formulation that you might run into is one that results in multiple solutions. So let's sort of look at what this sort of shapes up to be. So I'm going to go ahead and draw in the constraint equations. Let's see, so first one looks something like that. And again, the trick to doing these is just plug in 0 for one of the values and solve for the X-intercept or Y-intercept. 10, 20, 30, 40, 50, 60. All right, so this is the first constraint equation. All right. And we can add in the second constraint equation. Alrighty, so it's going to look something like that. Now, we do need to figure out the directionality, and again, we can plug in 0, 0 for each case, and we see that 0, 0 is in fact part of the feasible set. And in fact, I made a mistake. This should be maximize z. And so the half planes, or the feasible set for each of the constraints, in both cases points downward. So when we draw in our feasible set, especially, I'm not drawing in the non-negativity constraints, right? Because by now we should sort of know that we always want to stay above the x-axis and y-axis. Okay, so at this point, we can draw in our isoline corresponding to the cost equation. Right. So now, and I'm going to do one more thing. I'm going to label these guys. So this is constraint 1, and this is constraint 2. All right. So let's sort of draw in our isoline. So we can sort of figure that out a few different ways, but I think the easiest way is we know x2 has to go through 2 here, and this is going to go through 3 on the y. Okay, so now let's look what happens when we move this isoline up. It just so happens that it's collinear with the first constraint. And we can actually see this, right? So here we have 3 and 2. So we have 3x1 plus 2x2. And now let's look at this other equation, 1 over 40x1 plus 1 over 60x2. Now, if we are to multiply times 4, and I'll write up all the constraints. So let's do this. I'm going to multiply everything by 10, and then times 4 and times 6. And so that we get a lot of cancellation going on. We end up with 6x1 plus 4x2 is less than or equal to 240. Now the key part to note is that the ratio of the coefficients are proportional here. So we have 3 to 2, and then we have 6 to 4. And so it sort of makes sense that this isoline lines up with the first constraint. Okay, so what does this mean? Well, that means, in fact, your optimal solution is anywhere in this green part. Any solution that's on that green line is, in fact, an optimal solution. Okay, so it's the set of points between two of the extreme points, right? And so this is sort of interesting. So the other interesting part is, depending on which solution you take on that line, certain constraints will be active or inactive. So for example, if you pick this extreme point here, then constraints 1 and 2 are active. If you pick an extreme point that's in the middle of the line, then only one of the constraints is active. And then again, if you pick sort of this extreme point, then you have 2 of the constraints that are active. Always constraint 1 is active, but in this last case, the non-negativity constraint on x2 is also active. And in fact, I made a little mistake. So there's actually, the extreme points only refer to these guys. So anything that's in between those are not necessarily extreme points. So that's just something to keep in mind. Okay. So the next sort of problem that we're going to look at is going to be an infeasible one. And we're going to start with the same constraints that we had before. Okay, but now we're going to toss in 2 more, which is x1 has to be greater than 30 and x2 has to be greater than 20. All right, so right now we had this yellow feasible space just based on constraints 1, 2, and then the non-negativity constraints. So let's see what happens when we add in additional constraints. So the first additional constraint that we'll add in is x1 is greater than 30. All right, so at this point, so that's everything to the right of the line. The problem now becomes, this area here has become infeasible. So we can go ahead and mark that out, and we're left with only this small region in between the lines. Now, when we add in our final constraint, we're going to see that it gets even more restrictive. So adding in the x2 greater than 20, we have this inequality constraint, and the half space that is feasible is everything above the line. Now, as I said, the only feasible space prior to adding this last constraint was this yellow region. The issue becomes if we require that x2 is greater than 20, then this yellow region no longer becomes feasible. So in fact, we have no feasible points or solutions in x1 or x2 that would satisfy all the constraints. All right. The last possible case that you might encounter when using this graphical method is the infeasible solution. And so I'll sort of draw that problem here so you can get an idea of what to look for. And again, when you think about it, think back to this toy factory problem where we have the constraints that are holding the isoline of the objective function from going up, right? So it's got a ceiling. That's the case of the maximization. When we have a minimization problem, our constraints are typically below and our isoline is being held up. Right? So in the infeasible or in the unbounded case, what's going to end up happening is our constraints are actually going to be below the isoline corresponding to the objective function, and this is going to allow our objective function to be able to increase indefinitely, out to infinity. And for that reason, we say our linear program is unbounded. So let's go ahead and draw in these constraints. So I think the first one goes up to 6 here. Okay, so there's our first constraint. Again, I'm doing this guy right here. If we plug in 0, 0, we see that 0, 0 does not satisfy the inequality. And so, in fact, the set of points that are feasible for this particular constraint is anything that's above the line. Okay. If we take a look at the first constraint, we can draw that in. And it's going to look something like that. Right. And again, we can check, does 0 minus 0, is that less than 1? And it in fact is. So that tells us our feasible space is above the line. Now our non-negativity constraints are just as before. So here we have x2 greater than 0, and it's everything above the line. And we have x1 greater than 0, so it's everything to the right of the line. All right, so when we put this all together, our feasible space is this yellow area. Right. And as you can see, there's nothing actually holding back the feasible space. So the feasible space actually extends out to infinity in sort of like a giant cone. Right? So this becomes an issue when we start looking at the isoline for our objective function. Let's go ahead and draw that in. All right, so here goes our isoline. And as you can see, we can keep shifting our isoline up, and nothing is ever stopping it. It remains in the feasible space indefinitely. So in that case, we could essentially pick any x1 or x2, and that is in this yellow area, and it would satisfy the solution, but then we could find one even further away that would increase the objective function. So in that sense, our linear program is unbounded. All right, so with that, I'm going to wrap up. These are the classical cases that we'll encounter when we're using this graphical method in order to solve an optimization problem.